So over the next 3 classes, we're going to be talking about probability. Today I'm going to get through the basic probability concepts and then talk about combinations and permutations towards the end. I have some practice problems that we can do in class. Make sure we have some practice ahead of time before you do it on your own. For Chapter 4, there only is a quiz, but I did provide you with a practice homework if you wanted to go through that first. Doesn't count towards your grade, but if you need some preparation before taking the quiz, it's there. So in this chapter, we're going to talk about basic probability concepts, conditional probability, and how to use Bayes' theorem. We'll also talk about combinations and permutations at the end of class. So what is probability? It's the likelihood of a random event occurring. Anything that has a probability of 0 means that it's impossible to occur. It cannot happen. Anything with a probability of 1 means that you know it with certainty. Right? There's no deviation from it. Those two are the extreme values, but they're extremely uninteresting. Right? You either know they're going to happen or they're not going to happen. So all we care about things are in between. So anything between 0 and 1. The one you hear most often is that 0.5, 50-50 chance. Right? Flip of a coin. Now let's think about how these probabilities are created. One is a priori, meaning that you know of some prior information, either from a study, from a news article, that gives you the likelihood occurrence of being, say, struck by lightning, winning the lottery, something like that. Right, so this is based on prior knowledge in the population. The second one is empirical probability. So you go out and you get data, and you try to answer this question using that data. Pretty straightforward. The last one is subjective probability. It's probably the one we use the most often. Right? It's just your total random guess from your own anecdotal evidence of your life. When we do that, we usually see people use the certain focal points. So they'll use the 50-50, they'll use the 75%, they'll use the 40%. Something where it's a nice whole round number. Right. Subjective probabilities are actually quite bad. Humans are terrible at probabilities. For example, we all know the bad harms are associated with smoking, and smokers actually know that information better than non-smokers, and yet they're also way off about what is the likelihood of having cancer. Why? Because they tend to be really small. We're not very good with really small bets. So here's a simple example of an a priori probability. So I want you to find the probability of pulling a face card out of a standard deck of 52 cards. Now, in a standard deck of 52 cards, you have 4 suits. Each suit has 3 face cards to it. So how many total face cards do we have? 12. So then the probability should be 12 divided by 52.
3-ish.
So 0.23%. Right? That's just a straight probability that you can find. You know what the population looks like. You know what is available in that population. So you can find that by just doing straight math. Next one is an empirical one. So here we have folks who are taking stat classes, 160 of them. Folks not taking stat classes, 279. Of these, we can separate them between male and female. So then if I ask the question, what is the probability of a male taking statistics in this following population, what would you do?
The total of 439 by 76.
Not 76, those are females.
Oh, excuse me, 84.
84, right? So 84 divided by 439. And that would give us that roughly 19% of the folks taking classes are males taking statistics. Now we can split up probability into a couple of larger categories. One is just a simple event. Did it happen or did it not happen? And we only care about the one event, not that one event happening in conjunction with other things. Meaning that if I had a deck of 52 cards and I pull one at random, did I pull a red card or a black card? Nothing else. Not if the red card was also a face card. Right. The moment I add an additional condition to it, it becomes a joint event. I'm asking not only that it has to be a red card, but also that it has to be a red card of a particular type. A complement of an event is the opposite. So if you have taken logic before, you know that not statement, right? Complement event is the opposite. So if you pull a red card, the opposite in this case would be a black card. Now in probability, we also have something called sample space. It means something a little different in probability than it does when we're talking about a random sample. Probability means all possible outcomes. All possible outcomes are part of our sample space. So if we have a dice, a die actually, we need to include all faces of the die. All those are possible outcomes that could happen on a throw of a die. If we added another die to it, so we had dice, then we'd have to have all combinations of those. All those would be possible outcomes, and those are going to be part of our sample space. We need that in order to really find the denominator in these cases. All right? What are all the possible outcomes? Well, in terms of the die, there are 6 possible outcomes. In terms of the deck, there's 52 possible outcomes. And we can visualize the data in 2 ways. One is contingency tables, the other one is decision trees. Most folks use contingency tables, although management science in particular likes to use decision trees. Work your way down, see how it breaks out. We've already seen one contingency table before. You notice that we're going to have totals going down and also across the side. This helps us break up the different probable events into smaller ones. So, for example, we have 2 aces that are black, 2 aces that are red. There are 24 other cards that are black but not aces, 24 other cards that are red but not aces. All black cards should equal 26, all red cards should equal 26. When we sum them up, we should have our total sample space in both directions. The decision tree works the same way, except it starts with a particular node. And that node can be flipped, so if you wanted to start with aces and not aces, you could have done that as well. Here we're going to start with black versus red. So once you split it off between black versus red, you have to split it again by those columns. So you're going to have ace and not ace. And again, it should sum up to the same full sample size. So 2, 24, plus 2 is 24, should give us 52. Your friend in this particular chapter is the Venn diagram. I would try, as much as possible, to use the Venn diagram. You've probably seen it before, but it's the one that summarizes the data, I think, the easiest, because it's very visual. You can see it, you can write in the numbers, and it completes it. So make sure that you have 100% of the data in there. Now let's talk about what this Venn diagram means, and then I'll give you some examples. The Venn diagram, either written as a box or a circle, the one on the outside represents the total sample space. Right, so everything in here has a probability of 1 of occurring. Right, these are all the events that could possibly occur. Within there, you may have other circles. Now, those other circles are specific events that you're looking at. In this case, there's an event A and an event B. They don't have to intersect. When they do intersect, it means that there are some events that have a joint outcome. And that joint outcome means that both A and B exist in there. Just outside of that curve, only A exists. And just outside of this curve, only B exists. And outside of both of them is not A and not B. Right? So these are all other events that don't include A or B. If you can summarize your data like that, then you're essentially making these tables over and over again. Right? Because these tables tell you everything that's occurring. They're going to be really important when we talk about Bayes' theorem and conditional probability. All right, simple versus joint probability. The simple probability refers to the probability of a simple event. Well, it's the likelihood of pulling just one event. So whether or not you can pull a number out of a deck of cards and it happens to be a king. Whether or not you go driving today and you get into a car accident. That's an event. Right? Whether or not you get hit by lightning. Joint probability is not only do we get hit by an asteroid, but whether or not it lands in the ocean or on land. Right? So now it's 1, we get hit by an asteroid. 2, where did it happen? So that's the joint part. Now, mutually exclusive events are 2 events that cannot happen at the same time. 2 events that cannot happen at the same time are mutually exclusive events. So if you're picking just one card from a deck of cards, you can either pick a queen of diamonds or a queen of clubs or some other card, but you can't pick the same card at the same time. It's not possible. In most cases, you can't have a person with 2 genders, in most cases. So those are all going to be labeled mutually exclusive events. They're not complete complements of one another. All right, complement says just not a queen of diamonds, not a queen of clubs. That doesn't necessarily have to hold for mutually exclusive. It just means that once one event occurs, the other event can't happen. If you want to relate it to, say, sports, if you have a hit during a baseball game, during that same at bat, you can't have it now. You've successfully made it on base. If you're playing basketball, you've scored a bucket, at the same time, you can't have missed that bucket. Those are mutually exclusive events. So then we talk about collectively exhaustive events. So if you were to add a bunch of smaller events together, can you get the full sample space back? If you were to add all the little subsets together, can you get the full sample space back? So here are two examples. One where we include mutually exclusive events and one where we don't. So here we have aces, we have black cards, we have diamonds, and we have hearts. If we include A, B, C, and D all together, then they are collectively exhaustive. That means we can get the whole 52 set cards back. However, we're counting a couple of cards twice when we do that, which are the aces. All right, we have the aces for a couple of suits. We can drop the aces and still have all 52 cards back, just by using these subsets. In both cases, they're collectively exhaustive. It's just that in this case, we are counting one set of cards twice. Now this is going to be important when we want to start adding probabilities together. When we add probabilities together in this case, we can literally do the addition straight. We can say the probability of B is the probability of C, straight on through, and we'll be okay. For this one, we have to make an adjustment, because we're counting a certain set of cards twice. We want to make sure we remove that certain set of cards. Otherwise, we're going to have probabilities that are greater than 1. Or if we're going in the opposite direction, less than 0. And those are events that just can't occur. Alright, so now we've talked about simple probabilities, we've talked a little bit about joint probabilities, and now we're going to talk about marginal probabilities. A joint probability, again, is the occurrence of two events at the same time. A marginal probability is one where we have to add each one of those parts up. So you might be saying, well, what is all this? Alright, so here's an example of joint probability. We want reds and aces. Well, we know that we have 26 red cards, but only 2 of them are aces. Key part here is and. So if I want reds and aces, I have 2 cards, and I want to divide them by 52. Let's change the question slightly. What if I want red or aces? Now what's the probability?
28.
28. How'd you get it?
Half the cards are red, and the other 2 aces.
So half the cards are red, and then we have 2 aces left out. Alright? So you get 28 over 52. That's the OR. So the OR has to look for not just probability of being red, not just probability of being ace, but in some cases there could be overlap. Marginal probability is going to look at the probability of being ace and red, and the probability of being ace and black. Notice that these are the opposites, alright? This is the not category. So think of it back here with our example as this is the probability of A and the probability of B, plus the probability of A and probability of not B. And we can use all parts of B in order to get A back again. Now, the contingency table, what it does is it tries to find all the points of intersection. So if we really did a good job of collecting all the marginal probabilities, summing down the probability of B for each part of A gives us the full probability of B back. Same thing here with probability of B2, all the way back. In order for this table to be consistent, it has to be able to sum up to 1 on both sides. So going in the opposite direction, cross, we have probability of A1 and B1, plus probability of A1 and B2. Again, think of B2 as being not A1. So everything else is not B1, all right? When we sum them up, we should get the probability of A1 back. Same thing down here. So here's your probability review, and then we're going to start doing some problems. You heard me talk quite a while, but it's a little bit easier when you start doing these problems. Probability is a numerical measure of likelihood of an event occurring. Probability of any event must be between 0 and 1. If it is 0, it's impossible. It cannot happen. If it is 1, it will happen with certainty. The sum of all probabilities within a sample space have to equal what? Right, so those are all conditions of the world, if you can think of it that way. Here's the general addition rule. If the probability of A or B is going to be equal to the probability of A plus the probability of B minus A and B. If the two cases are mutually exclusive, the addition rule still holds. And what's the probability of A and B? 0, right? There's no intersection. At no point those two things intersect. So going back to our general addition rule, if we have the probability of being red or ace, which we just did a second ago, we'd have the probability of being red, which is 26 over 52, plus the probability of being ace, which is 4 over 52, minus counting the red ace twice. So subtracting off 2 over 52, leaving us with 28 over 52. Alright, so now for conditional probabilities. For conditional probabilities, before we talk about the math, what you should think about is, first you start off with a big sample space, and I tell you that I only want to look at a subset of that sample space. Right? So let's say that this full sample space are majors in the College of Business, and I only want to look at accounting majors. What I'd first have to do is find what is the probability someone is an accounting major, and that becomes my new denominator. That's where the complement comes from. That's where this conditional probability comes from. Right? It becomes the new denominator, the new sample space. And then I can ask questions about accounting majors specifically. So given that you're an accounting major, what is the likelihood that you're female? Right? That's a different question than saying, what is the probability of being both female and an accounting major? And that second question, I'm asking that over the full denominator of students in the College of Business. In the first question, I'm saying, now that I know that you're an accounting major, so let's throw everyone else out. What is the likelihood of you being female? That's where conditional probability makes a difference. So, in math, this is what we're doing. This is the probability of A given B, so conditional on B. To do that, we have to put the right sample space in the denominator. The right sample space in this case is going to be that you're in B. In the numerator, we're saying, well, what is the likelihood of being both A and B? So what is the likelihood of being both female and an accounting major over the probability of just being an accounting major? The thing about this is that we can flip this one around. We can also write the conditional probability as given A, what is the likelihood of being in B? So given that you're female, what is the likelihood that you're an accounting major? The reason we can write that both ways is due to a multiplication law. So here's one example. Let's say you have a bunch of used cars. 70% of them have air conditioning, and 40% of them have CD players. Only 20% of them have both air conditioning and CD players. So for a second, go ahead and draw out the Venn diagram. And what I want you to do is put the correct probabilities in each one of the areas. Meaning, what is the probability of being only AC? What is the probability of being only CD? What is the probability of being both AC and CD? And then what is the probability of having neither? It should be out here. Do that first, and then I'll show you why it's easier to do it that way, and then find conditional probabilities. Alright. So if you do that, you end up with 0.2 divided by 0.7, and you get about 29% of cars who have air conditioning also have a CD. Right, so 29% of cars that have air conditioning also have a CD. Notice that I have to put on that condition. It's not 29% of all cars. Only those that have air conditioning have a CD as well. Now we can do it the flip side. We can say, given that you, we can do it this way using a decision tree. You can start with all cars. You can say how many have air conditioning, 70%. How many don't have air conditioning, 30%. And from there you move on to the next part. How many have CDs? And how many do not have CDs? Notice that in those conditional probabilities, 0.7 is sitting in the denominator. So you have 0.2, those that have both CDs and air conditioning, divided by 0.7, those that have air conditioning, over 0.5 divided by 0.7. 0.5 just comes from 0.7 minus 0.7, I'm sorry, 0.7 minus 0.2, that gives us a joint probability of having air conditioning and a CD, having air conditioning and not having a CD. We do the same thing down here. It's not having air conditioning and having a CD, and not having air conditioning and not having a CD. Notice that each one of those endpoints are each one of the numbers that we have here. Because all these are joint probabilities. Right? This one says having both. This one says having only AC and not CD. This one says having CD and not AC. This one says having neither AC nor CD. So if you have the Venn diagram, you already have all the joint probabilities. This is just flipping it over and starting with CD. At the end, we should get the same numbers. All right. So now that brings up another concept that's called independence. Now, independence says that given that you know B, that gives you no information about A. Let me say that again in words. Given that you know B, that provides you with no information about A. You see that, and it might want to trick your brain into thinking that A and B are mutually exclusive. Mutually exclusive is actually an extreme form of dependence. Think of it this way. If you know you're in B, and A and B are mutually exclusive, what does that tell you about A?
Being there.
Huh?
Being there.
Yeah, you're not in A. You know you're in B, you're definitely not in A. So the probability of A has to be 0. Even if you know you're in B. So mutually exclusive is actually an extreme form of dependence. Independence says if you know you're in B, it doesn't tell you anything about whether or not you're in A or B. So these guys are actually going to intersect. If they don't intersect, then you know the moment you're in one, you're not in the other. But these folks will intersect. All right, so the probability of A and B will be equal to the conditional probability, but that conditional probability doesn't give you any information. So since it doesn't give you any information, it's just the multiplication of the two. The probability of A times the probability of B. So in the case of marginal probabilities, if A and B are independent, all you're really going to end up doing is summing up all of the individual probabilities. So now it brings me to Bayes' theorem. Now Bayes' theorem is a harder concept. People use it all the time, kind of subconsciously. We do it when we have a particular view of the world, then something happens. And that thing that happens changes our view of the world. It doesn't change it dramatically, but changes it just enough that we update our beliefs about what's going on. I use this in my dissertation with folks who are in clinical trials. They're sitting there, they're taking a drug. If they think they feel better, right? If they think they feel better after taking the drug, even though they started knowing that there's a 50-50 chance they're either going to have the drug or not, if they feel better, do you think that they're going to increase their probability of being in the treatment group? So what they're doing is they're taking a new piece of information and they're adding it to an old piece of information to update their beliefs of which group they think they're in. So we went back to this conditional probability. What's going on is they're saying, what is the probability that I'm in the experimental group given that I feel good? That's the question they're trying to answer. Given that I feel good, what is the likelihood I'm in the experimental group? Well, the more I feel good, the more likely I'm going to be in the experimental group. So here, Bayes' theorem is used quite a lot by folks to do exactly that, update beliefs. They're saying, first, this is my probability that I think I'm getting the drug, regardless of anything else, which was the original 50-50. And then this is the probability that I'm feeling good, given that I think I'm in the experimental group, divided by all different other groups that exist. So first, you already know this is the conditional probability, right? This is the probability of A given B is equal to the probability of A intersect B divided by the probability of B. That's what we just did last 5 slides. But then, because of marginal probabilities, I can write the probability of B as this long thing. I can break it up into each one of the little parts. So since I can do that, I can get to this equation here. Let me give you an example first, and we'll go from there. You guys ever seen Let's Make a Deal? game show, Let's Make a Deal? Alright, so there is a very popular game in this Let's Make a Deal called Monty Hall Problem. It's when you are presented 3 doors, and you get to choose a door. You choose a door, and you know that behind one of the doors is a car, and behind the other 2 doors is a goat. Alright? So at first it feels like you have a 1/3 probability of winning the car. You choose a door, and then before they reveal the second door, they always show you one goat after you've chosen a door. They ask you whether or not you want to switch. Now, you might want to think logically and say, but I had the same probability. It's still 1/3. Right? Turns out that, according to Bayes' theorem, you're always better off switching. You're always better off switching. Right? On average, that is. You'll lose in some cases, but you're always better off switching. This video will show you how. And all it does is use his Bayes' theorem in order to do it.
We apply that Bayes' theorem in that specific situation.
Yeah.
And see it actually work.
Yeah. Most of the time. On average, it'll work.
Yeah.
They'll explain it. So you're always better off switching. Because 2/3 of the time, you pick the wrong door. And this has been a problem that it seems so simple and so obvious, but it's baffled people. Mathematicians have tried to go back and prove it wrong somehow. And even then, they go back and they're like, no, it's still right. Alright. Now I'm going to give you a different example of Bayes' theorem. Actually, 2 more. Here's one with a drilling company. The drilling company has estimated a 40% chance of striking oil for a new well. So that's an overall probability, right? The detailed test has been scheduled for more information. Historically, 60% of successful wells have had detailed tests, and 20% of unsuccessful wells have had detailed tests. Given that this well has been scheduled for a detailed test, what is the probability the well will be successful? So let's try to give these things some names so we can write this out as an equation. All right? So we're first told that a drilling company has estimated a 40% chance of striking oil for a new well. This is 40%. Next thing we're told is that the detailed test has been scheduled. 60% of successful wells have had a detailed test. Let's call this probability of success conditional on test. Alright? Given that you've had a test, 60% of these guys have been successful. The next part says 20% of unsuccessful wells have had a detailed test. So this is now saying, I'm going to write this as not success, just so we can be a little clear here. Right? Given not success and test, this is equal to 0.20. So it says, given that this well has been scheduled for a test, what is the probability that the well will be successful? So here is probability of success, 40%. That's what we got here. Probability of failure, or not, S, is 60%. And we want to know what is the probability of success given D. So 60% of successful well. So we want to find out what is the probability of success given a detailed test. Well, we know that this is equal to the probability of success intersecting a detailed test over the probability of a detailed test. Now we don't know this guy immediately. Right? None of this information up here tells us this immediately. But we can find this because we do know the probability of D given S times probability of S is equal to probability of S intersect D. Right? We know this. That was all that math we did a couple of boards ago. And this, we're given that. So here is our detailed test. Here's success. So this here is going to be 60%. Right? We know the probability of success, 40%. So we can now find that intersection by just multiplying the two. That gives us 0.24 up here. What about the bottom part? What is the probability of success? I'm sorry, of a detailed test. So think back to marginal probabilities. I have to sum up, if I sum up the parts, I can get the whole back again. Now I have some parts, right? I have probability of a test given a success, and I also have the probability of a test given a failure. If I have successes and I have failures, don't they make up the full sample space? So if I sum these up, what do I get?
28.
I get 80%, right? So 80% would be the probability of a test. So here we go. We have our 0.24, our 0.24 here, our 0.2 times 0.6. So these are our failures. Take that ratio, and we get 67. So we started with a prior of 0.4 and 0.6. That's what we started with. We were given new information. The new information was you had a detailed test. So this is going back to what I was saying with the patients. They knew that their prior was 0.5 and 0.5 getting to the treatment group, right? Then they felt good. How did they update their beliefs given they felt good? So here is, how do you update your beliefs given that you had a test? Given you had a test, how do you update your beliefs? So we want to know, well, what was the revised probability of a success given that you had the test? And those were the steps that we followed in order to get to the 0.667. So that new piece of information is what allowed us to update our beliefs. Alright, here's one that you can try to do on your own before we do combinations. But according to Wikipedia, women whose partners use male condoms experience a 2% per year pregnancy rate with perfect use and an 18% per year pregnancy rate with typical use. According to a survey, condoms are only used correctly 60% of the time. That's an actual statistic. What is the overall probability of pregnancy when a condom is used? So as you're doing this, think about what are the conditional probabilities. That 2% is given that you use it perfectly. Right. Given that you use it perfectly, in other words, you have appropriate use, you have a 2% chance. And then given that you don't use it perfectly, you have a probability of 18%. And I want you to find me the overall probability. Right. Just to be clear, this is what we have. The probability of getting pregnant given that you have perfect use is 2%. Probability of getting pregnant given you have imperfect use is 18%, and the probability of perfect use is 60%. I want you to find me the overall probability of pregnancy.
0.084.
0.084. Given that you just grab someone at random and you don't know their use level, there is almost an 8% chance in a year, not that one time, in a year, of pregnancy. Right? The box says what it says. That's what's perfect use. Then you throw in humans into it, and perfect use goes away because of other reasons. Right? So there's nearly an 8.5% chance of pregnancy over a year, even with condoms. So now what I want to talk to you in this last 4 minutes, so we'll have to start this up next time, is on combinations. And combinations are used a lot in discrete probability. So this asks you, what is the likelihood of making a particular sandwich, or what is the likelihood of a 4-digit extension? One of these things, all right? So here we have bagels. You can have plain bagel, egg bagel, wheat bagel, onion bagel, and then you can add meats to it. What are all the possible combinations between bagels and meats that you can have? All right, we're going to choose one for each category. 16. All right, what about eggs and meats?
12.
Sorry. And then the last one, you have 4-digit phone extensions. You can have anywhere between 0 and 9 for each one of those.
24.
We have 0 and 9 for each one of those.
40. 36. Oh, no, it's
You can 0, 0, 0, 1, 1, 1, 1, 2, 3.
6,561.
Not quite. About 10,000.
That's not
10 times 10 times 10 for 4.
Yeah.
Wow.
Alright, because you have to include 0, alright?
Okay.
You have to include 0, so it's going to be 10 to the 4th. 10 to the 4th. Now the way you did that up here is you just did straight multiplications, so we're only doing one from each. If we had multiple meats, then there would be more combinations. Here what we were doing is we had recognized that along each column level there were 10 options. Alright? And there were 4 places that we could put those 10 options. So it would be 10 times 10 times 10 times 10, or 10 to the 4th. All these are examples of combinations. Right? And each one of these cases, in the first 2 cases, the order didn't matter. Right? It didn't matter if you picked the bagel first and then the meat. That didn't matter. For the last one, the order matters. The last one's called a permutation. Right? 1, 1, 2 is different from 2, 1, 1. So there the permutations matter. Deal with these functions. First thing we need to know is what is a factorial. Whenever you see 5 or a number behind an exclamation mark, it means to multiply all those values all the way down to 0. And the factorial of 0 is 1. It's a weird rule. Factorial of 0 is 1. Right? We're going to use this in order to come up with our combination formula. So at the end of the last class, I was talking about a list of items and how we can combine these lists of items in different ways. First way that we can use a mathematical shortcut to find different combinations of a list of items is permutations. Now permutations, they tell you all different types of combinations, but the order has to matter. So think of things like telephone numbers, your social security number, your password, your name for that matter, because it's a combination of letters where the letters matter, their order matters. All those are forms of permutations. At the end of last class, we introduced this idea of a factorial, how we use that factorial in the setup. If we want to find the permutation of 7 items, given that you take 3 items at any one time, where the order matters. All right, so to give you an example of what I mean by the order matters. Actually, let's let you do this example here. How many different ways can 4 letters from the alphabet be arranged? So if we have 26 letters in an alphabet, we know that the big N here is 26. If we subtract off those 4 that we're choosing, then we're going to have 26 factorial over 22 factorial. When you multiply through, there are 358,800 different permutations of 4 letters using the alphabet. Now, they don't have to make any sense, right? For example, A, B, C, D would be 1. They don't have to make any sense, but those are different combinations of letters that you can use. So now, on to combinations. In combinations, the order does not matter. So we make a small adjustment to the permutation formula. We still include the first part, which is that 7 factorial divided by 7 minus 3 factorial. Still include that. But now we need to adjust that we are overcounting for these guys. Well, they're so there. We're overcounting for the different orders. And we do that by including a term that says how many we're selecting. That's where that 3 factorial pops up. So if we go back and we do this again, where I have 3 letters and I'm picking all 3 letters, right? I should only get one word, one combination. So 3 factorial divided by 3 factorial, 0 factorial. Without doing any math, you can see pretty quickly this is going to equal 1. Right? So this multiplication term right here, that's added on a combination, gets rid of the order problem, permutation. Alright, so here's one example. There are 12 different colored cubes in the bag. How many ways can randomly draw a set of 4 cubes from the bag? So here your big N is going to equal what? 12, and your little n is going to equal? 4. Let's go do it. So there are 495 different ways that you can do that. Alright, so now we're going to do a real world application. What are the odds of winning the lotto? Alright, you can use a combination to figure that out. The odds of winning the lotto. Right, because the order doesn't matter when they come out. If the order mattered, then it'd be worse. Right? The order doesn't matter when they come out. Alright, Kentucky Cash Ball. This one's a little bit harder. Kentucky Cash Ball, then you have 2 steps to it. First step is you have to pick 4 numbers between 1 and 33. Right? The next step is you have to pick this extra number between 1 and 31. So we have to split this up into 2 parts. Let's do the easy part first. What is the likelihood of getting the right number if you're picking one number between 1 and 31?
1 divided by 31.
That's it. Just 1 divided by 31. So let's get that out of the way. That's over on the side now. Alright? 1 divided by 31. That's one additional probability you have. That's sitting outside this harder one. So now this harder one is just a combination. It's saying pick 4 numbers between 1 and 33. Once you pick them, you can't replace them. It's not like you can pick 33 4 times. Alright? Once you pick them, they're gone. So tell me, how many different combinations can you pick 4 numbers between 1 and 33? So, about 41,000 different combinations. Alright? Alright, we're choosing 4 numbers out of 33 possible numbers without replacement. So once it's gone, it's gone. So you get this 40,920. You think, oh, that's not too bad. But we still got to multiply that times the 1 over 31, right? So when we do that, when we multiply that, the likelihood of just getting the first part is 1 over 40, roughly 41,000. You multiply that by 31, so then the likelihood of winning becomes 0.000000788. To make that an odds, that's a 1 in 1.2 right now, 1.2 million chance of winning. That means you have almost as good of a shot at being hit by lightning twice than winning the lotto. I could do Powerball. That's worse. Much worse. Because you have more numbers and you have the Powerball. But you can see it's pretty hard to win the lotto. In terms of a fundraiser, it's great. Alright, so let's make sure that we've learned some stuff along the way. Let's try to answer these 4 questions. 6 different books will be displayed in a library window. How many different arrangements are there?
720.
How'd you get there?
6 factorial.
Yep, 6 factorial. Right. The code for a lock consists of 5 digits. The last number cannot be 0 or 1. How many different codes are possible?
80,000.
Yep, 80,000. So, for the first 4 digits, you still have all of the 9 possible digits. But for the very last digit, you only have 8 possible ones, because you can't include 0 or 1. So that's going to be, in case we missed that, 10 times 10 times 10, and then times 8. Alright, the 3 best essays in the contest will receive gold, silver, and bronze. There are 10 essays. In how many ways can the prizes be awarded? Now, quick question, is this a combination or permutation?
Permutation.
Permutation, right? Because the order of when you win matters. How much?
720.
720. That's right. Alright, so you have 10, choose 3. So all you have is the 10 divided by, what's that, 7 factorial. And then you go ahead and do your math. And then the last one, in a talent show, top 3 performers of 15 will advance to the next round. How many ways can this be done? Is this a permutation or combination?
Combination.
Combination, right? The order doesn't matter as long as you make the cut. What do we got? Someone new.
455. 455.
455, that's right. 455. Good job. All right, well, that is the end of the intro chapter.